Hi everyone, welcome to lecture 5 of Hardware Software Codesign for Edge AI, and in this lecture we'll be discussing pruning. So we've already discussed quantization in lecture 4. I hope you've got good understanding of what is quantization. In pruning we'll be discussing with beginning in what is pruning actually, what is pruning, and then we'll discuss about granularities of pruning. And then we'll be looking at certain criteria for selecting the weights which have to be pruned, criteria for pruning. So this is going to be our lecture plan. I have summarized it in another slide, so let's move forward. So before we begin, I just want to tell you about the ML Perf. So just like the Olympic Games are going on, so ML Perf is the Olympic game for AI computing, and it has two divisions, closed division and open division. So in this, what you see right now is the submission of BERT, and what you can do in closed division is you cannot change the model. So whatever the original model of BERT is, you have to use as it is. And major companies like AMD, NVIDIA, and Intel, all the hardware acceleration companies, etc., whoever is into Google, whoever is into actually hardware, manufacturing of AI inferencing chips. In fact, Amazon has also started in its own inferencing chips, AI inferencing chips. So you cannot change the model. Whatever the model you are given with, you are just supposed to actually run that model on your hardware and give the performance of it. So NVIDIA won that obviously with 1029 in the closed division, and in the open division you can do all sorts of ML optimization, and with the same hardware, whatever you are doing in the closed division with the same hardware, but now you're allowed to do all sorts of ML optimization on the model itself. So in this category, Intel won, and that's something really nice, that their model optimization, which they call it as OpenVINO. So it was a close competition in the open division, but they won by some margin. So that's the Olympic game for AI computing. So we're looking right now at the submission of NVIDIA. So what they did was, this is just like setting up the motivation for why pruning and then quantization and the ML optimization really works. So in the offline scenario, if we would just do quantization, QAT stands for quantization aware training, and we just do quantization basically and then run the inference. Then while maintaining the accuracy in all three cases, the model size was initially 607 MB. This is what the model was after doing the quantization. And this is on the BERT again, on the BERT model. Then when we do pruning and then quantization, so quantization plus optimization in closed division along with pruning. So pruning plus quantization led to a speed of 2.6x and the model size was around 177 MB. Just note that these two things are not like one-to-one correlated. Like generally, if the model size is lower, you'll find this increase in the speed, but it will not be of the same ratio, because speeding up is dependent entirely on the hardware parallelization, and model size is just model size, which is determined by number of weights and activations which you have. Then we have, once we do quantization, pruning, and then along with distillation. So pruning, distillation, then quantization led to a speed of around 4.5x. So this is an interesting thing to note before we actually begin with pruning. Let's setting up a motivation that you can win in the ML Performance Olympic game, right? So today we will introduce neural network pruning, which can reduce the parameter count. So it directly reduces the parameter count. In quantization, what we did for each weight, if it was FP32, we tried to reduce it down to FP16, let's say, or FP8. But here we'll cut down it entirely. Like, it's not just reduction, it's like entirely removing the weight in itself. So it's very, very effective when used properly. So you see that pruning of synapses, certain synapses itself will be gone, and pruning neurons mean that this neuron which is present here is not present here. So all the weights associated with it, coming from the backwards and coming from forwards, all of them are gone. So, and it can improve the performance by huge degree, decreasing the storage requirements, improving computational efficiency of neural networks. And we'll go through all steps of pruning and introduce different granularities and criteria of neural network pruning. So only when we understand the granularity, what are different granularities, will we be able to set the appropriate criteria. Okay, so again, just this slide is very important. Why? Because data movement, more memory references, more energy, and we want to save energy, we want to save data movements, we want to actually save on memory referencing. So if you see that out of all the operations, 32-bit SRAM cache transfer and 32-bit DRAM memory is most energy consuming, and this is what is actually draining energy from our phones. The more we try to open the file explorer or the apps, like just the UI of the system is not draining the energy so much. But whenever we try to do memory referencing or play the video, so videos have to be transferred from the memory, DRAM memory or the SRAM memory to your display. So display is also running the consuming the battery, but it's what is memory referencing is what is actually draining away the energy from our phones, and the more memory referencing we do, the more energy is reduced. So let's discuss what is pruning, and right now we have two images in front of us. We'll call this as dense neural network and we'll call this as sparse neural network. So sparse in English word basically means that something which is located in at not a contiguous blocks. According to the Google, it simply means dispersed or scattered, right? So you can see that all these things are more scattered and dispersed. And pruning happens even in the human brain. So like for a newborn child, so this was in a research paper, that the number of synapses which we have, which are basically the connections as we've seen in lecture 2. So a newborn baby has around 2500 synapses per neuron, and around the age of 2 to 4 years old, it peaks up to around 15,000 synapses. And this is the time when the child starts to learn and train his mind. So initially the neurons, the synapses just keep on increasing, and then once the child is getting trained, the synapses are pruned, some of the synapses are cut. So that is what actually trains the child and gives up those electroencephalography patterns which you see, like when he hears a certain sound, so a certain signal is sparked inside the brain, a certain pattern of energy is sparked. So those things are trained by repetitive training of the child, and it gets stabilized around 7,000 synapses per neuron in the adulthood. So basically neural network pruning, what it means is make neural networks smaller by removing synapses and neurons. So pruning synapses and pruning neurons, this is what pruning means. And we'll choose a very simple criteria for pruning. So take a moment, guess what weights, what synapses would you try to reduce if given an option? Answer is simple, the ones which are having no effect on the final output. So those which are tending to 0, you will try to remove them. It's a very simple definition of pruning. It's a very simple criteria of pruning. We'll mathematically formalize it in future slides, but as of now you can take this as a simple criteria. So considering that this was our original dense neural network and having the accuracy percentage, whatever is the original baseline accuracy, we're starting to measure from that, and the weight pattern looks something like this. Out of here you see many weight values are close to 0. So what we do is we prune the connections. So if the more we start to prune, the more we start losing the accuracy, and so we need to compensate for it, right? So here you can see that we've removed all the weight values which are close to 0, and that's how the more we reduce from the point of 0, the more we are pruning, the more the pruning percentage is increasing and more the accuracy is dropping. So prune connections is leading to accuracy loss. So in order to actually compensate for the weights, what we do is we fine tune the weights again. So whatever data set we have trained our neural network on, we again feed it, and all these weights have the degree of freedom to compensate for the lost weights. Like they can retrain themselves in order to regain that accuracy. So, and in some cases you see that the accuracy is also increasing for some time until ultimately falling again back. So with that we can again prune up to around 80%, and the weight distribution starts looking more normalized and more distributed, not like an abrupt cut which we have made previously. So this is after retraining of the weights. But you see that some weights again have come back to the original 0 position. So what we do is we can do this whole process iteratively, and that gives the extra, squeezes out that extra bit of around 90% you can see with minimal loss of accuracy. We don't want to lose accuracy more than 0.5%. No point in like pruning if your accuracy is losing. What is the point in that, right? So this process we go on repeating, and that's how we can do the entire pruning process. So here we have number of parameters and the max, and before pruning, after pruning, and what is the percentage of reduction. So AlexNet, which was around 2012, as you know, before pruning the weight, the model size, if it was around 61 MB, then after pruning we can get a reduction of 9x while maintaining almost the same accuracy in the limit range of around 0.05%, as we had seen here, 0.5%, sorry. In that range we can prune and get down to around 6.7, which means reducing up to 9x, reduction of around 9x. Now depending on the model, the larger the model, like VGG16 is a huge model, it's a huge model, 138 MB, and therefore there is a lot of redundancy also in the model. There's a larger room for reduction as well. So it gets reduction of around 12x, but the reduction in max is around only 5x. So don't just go on to the like number of parameters getting reduced, we also have to observe the number of max, and it's not just also number of max which determines the speed or the performance. It's how much parallelization you're able to do, and this will become more clear in some of the futures and some of the slides which we see down this lecture. So GoogleNet, similarly you can see 3.5x. So one particular example of this is SqueezeNet, and the model is so efficiently designed, it's similar to AlexNet, like a very optimized version of AlexNet, and the model itself is around 1 MB, and after pruning we just see a reduction of around 3.2x. So more the model is efficiently designed, the lesser the chances of pruning it. And some examples of there's this Neural Talk LSTM, that after pruning this large language model, what were the results before and after that. So before it was saying baseline was that a basketball player in a white uniform is playing with a ball, but after we pruned the large language model to 90%, it said a basketball player in a white uniform is playing with a basketball. So not much difference you can see, like the keywords were maintained. A brown dog is running through a grassy field. After pruning it said a brown dog is running through a grassy area. So again, like it's making sense, not an issue. A man is riding a surfboard on a wave, and after pruning it said a man in a wetsuit is riding a wave on a beach. So okay, still acceptable. But here you see that when we pruned it 95%, so before it said a soccer player in red is running in the field, and after that it said a man in the red shirt and black and white black shirt is running through a field. So it almost starts like in the drunken state, that how a drunken man would describe this image. So before 2016, so one of the important papers in this area which described pruning was published in 2015-2016 time frame, and after that there was another paper called as Efficient Inference Engine, and which described about pruning and sparse neural networks, that how to optimize machine learning based on pruning and making sparse neural networks. But the mathematics of it was laid down back in 1989 with optimal brain damage. So, and it's quite commonly used in industry. So this deep compression paper which you see by Song Han, which is a very famous professor, one of the major references in these courses, in this lecture. His work is being used in NVIDIA and AMD altogether. So you can see that in 2016 there's an efficient inference engine which was designed, and we'll go over through this later, but basically it takes in the input image and the compressed model, basically the machine learning model and the input image, and then what it does is it encoded weight, relative index and sparse format. It produced criteria. So we won't go into this algorithm right now, what I would want to show you is that if there is a dense matrix right now, and here it is color mapped, like all these things which you see in white are close to 0. So if we remove those weights entirely, so this is a dense neural network and this is a sparse neural network, so it gets converted to a sparse matrix. And I'll tell you what 2 is to 4 sparsity means, but in Ampere architecture of NVIDIA, they supported sparse matrix multiplication, because no point in multiplying 0 with a 0, right? Why are you unnecessarily wasting a MAC and a whole cycle in parallel along with other multiplications? So this proposed an algorithm for doing sparse matrix multiplication, that only doing matrix multiplication of those elements which are non-zero, and they introduced 2 is to 4 sparsity in A100 GPU, which lead to 2x performance and 1.5x speed up on the BERT model. So it's 2x effective, and this is the optimized tensor core. There are many algorithms related to sparse matrix multiplication like SP arch and SP attention, like SP10. And this is another efficient, this is the FPGA implementation of the efficient inference engine back in 2017. So again, the pruning is in the industry as well. There was, when I worked at AMD, previously it was Xilinx, and it got acquired by AMD in I think 2022. So that was the time, and I happened to work on this AI optimization and prune neural network. We had to deploy the test cases and see how this pruning algorithm is working. So they actually use directly from this paper of deep compression, and it's a very simple methodology which they choose, which I'll be explaining in this. It's not like a rocket science or anything. It's a very simple, if you have a dense neural network, you can get converted into prune neural network while maintaining FP32, FP32. It's available right on their website. I would highly suggest to go ahead and check it. So how should we formulate pruning in a more mathematical terms? So look at this slide. Don't get scared by the mathematics. It's like very simple machine learning mathematics. It's a field called machine learning optimization, in which we lay down an objective. So here the objective is that, in fact, let me explain you first with this slide, with these diagrams actually. So here with the original input x coming in, and the weights, original weights as w, we want to minimize this loss function while training. We want to minimize that. So L represents the objective function for neural network training, and x is the input, w is original weights, wp is the prune weights, and this notation wp 0 calculates the total number of non-zeros in wp, and n is the target number of non-zeros. So what we actually want is that in the mathematical formulation, if this is our objective function, so this is how it is said. We want to minimize the loss function subjected to a particular value of weight matrix P, subjected to the total number of non-zeros, which is also known as L0 norm. L0 norm is basically represented as this. Whatever you mentioned, this is the L0 norm, which calculates the total number of non-zero elements. Okay. Later on, we'll see what L1 norm, L2 norm as well in the lecture. That time I'll explain that. But for now, L0 norm, you just understand, is represented by this, and this subject basically says that the total number of non-zero elements in the final weight matrix should be less than a number n, and that is how we start optimizing it. That is where we start to optimize, that we want to minimize the loss function subjected to this condition. Okay, how it is done, how this optimization is actually come into play, this is more related to mathematics, but we're just formally defining the mathematical function, formulation of this. I hope all this is clear, that what is the loss function, x is the input to the neural network, is the original set of weights. We've covered all these things. You can pause the video and check it out. So how to determine the pruning granularity? So in what pattern should we prune the neural network? So you see on top of it that there is very fine granularity. There is no structure or pattern to what weights we are reducing or cutting down. As opposed to, you can see in the coarse granularity, we have a certain pattern, like, we're having a pattern, a set of 2 or something like that. So that is coarse granularity. We'll see the pros and cons of all these things, but let me just walk you through the entire lecture plan as of now. After understanding the pruning granularities, we determine the pruning criteria, that which synapses or which neurons to ultimately prune based on the granularity which we have chosen. And then we'll look into the pruning ratio, that what should be the target sparsity for each layer, that what should be the pruning ratio actually, how much to prune. And finally, we'll look into fine tuning the trained prune network to improve the performance, how to do that, and it will be a mathematical function again which we'll look into. So in this section, pruning granularity, will be looking at pruning can be performed at different granularities from structured to non-structured. So this is a simple example of a 2D weight matrix, and it's 1, 2, 3, 4, 5, 6, 7, 8, 8 cross 8 matrix which we have. So if we do a very fine grained unstructured pruning on a very simple criteria, that whatever weights are close to 0, let's just remove them. And there is no pattern which we are following, and it's completely random. Like, all we are ensuring is that total number of weights after we prune basically the L0 norm should be less than a particular number n. So basically you cannot prune the entire thing, which will not even make sense, but you want it to reduce to a certain number, like you want to count all these red blocks, and that should be less than a number n. So this is a fine grained unstructured granularity, and more flexible because, and it's very easy to perform, but very hard to accelerate because it is very irregular. As we discussed, that ultimately it simply means we have to multiply this matrix with something, but a sparse matrix multiplication is not an easy task. How will you know that, okay, unless you actually multiply it, how will you know that it is 0? Or so there are certain things which we'll do, you'll see it later on, as opposed to coarse grained or like structured pruning. So this is less flexible pruning and but it is very easy to accelerate, because after you've pruned the entire, let's say the row, you can make another matrix and you can just treat it, that new matrix, like a dense matrix, and we have obviously have very good hardware inferences, hardware inferencing engines for dense matrix multiplication. So let's discuss a little bit of mathematics about pruning at different granularities. And in the case of convolution layer, so previously what we saw was just a fully connected layer, like we had seen that CO and CI, that if there are certain nodes in the input layer and in the output layer, then your weight matrix is nothing but CO comma CI. But we have more flexibility when we are doing convolution operations, as we have 4 dimensions, not just CO, CI, but we have the kernel height and the kernel width as well. So we have the input channels, or the number of channels which determine the depth of the filter, and the kernel height and the kernel width, which is our choice what we make, and the output channels which we have, which is something we want, like something which we can choose again, how much we want in the output channels, which determines basically the number of filters we are choosing. So the 4 dimensions gives us more choices to select pruning granularity, and let's look at this right now. So let's say that our input channels is 2 and our output channels are 3, and for the kernel height and the kernel width is 3 and 3 cross 3. So basically we can actually look at each of these 3 cross 3 2D matrices if we try to plot it down in this. So this is input channels, and these are the output channels, and these are the individual layers which we are seeing. And if we choose this notation to describe our weights in the convolution neural network, so basically this is effectively what? This is effectively the weights which we had seen in the neural network, right? Based on the different filters. So these are the different filters, and these are the channels. So in a very fine grained pruning, you will see that again the very easy criteria, it's highly irregular, and it's highly irregular. Sorry, it's highly irregular. As opposed to, let's go sequentially, there is a more pattern based pruning in which there is a pattern which is followed, and that's a very interesting question actually. What patterns do we observe, or how we can effectively code that patterns? And in a moment we'll play a small, like, quiz session in which you'll have to pause the video and guess it for yourself. To a more vector level pruning in which we're pruning the entire row altogether, and a kernel level pruning in which the entire kernel itself is pruned, that this whole kernel is made zero, that particular layer is made zero, versus channel level pruning. All together the whole channel is actually pruned away. So we go from irregular to regular. The more regular we are, the easy to accelerate the pruning process and speed up is possible. So again, don't forget the dimensions we are choosing, like how we are describing it, that Ci is equal to 2 and Cu equal to 3, and for each of these, Kw, Kh is describing the single layer in that filter. So what are the pros and cons of the irregular pruning, or as we call it, the fine-grained pruning? So let's look at this slide. That in fine-grained pruning, the case we showed before, there's a flexible pruning indices, that whatever weights are less, you just reduce that. No more, like, no hassle or anything, like you just reduce it. But using a reduction in number of parameters doesn't necessarily mean acceleration, until unless it can be parallelized in GPU. As I've told you already since the start of the lecture 2-3 times, that just reducing the number of parameters does not guarantee you acceleration, right? So you usually larger compression ratio, since we can flexibly find redundant weights, but it will not lead to speed up, but it will give you a good compression ratio. Can deliver speed up on some custom hardware, but not on GPU easily. If you design like a custom hardware, like an efficient inference engine, which takes into account those fine-grained pruning, it'll be easy. But GPUs are meant to perform tensor operations at huge parallelism, like at heavy-duty parallelism. So it's not easy for them, as opposed to a pattern-based pruning. So observe this pattern, or let's look at this slide. So in a more pattern-based pruning, without reading this slide, try to pause the video, and given this dense matrix and this sparse matrix, pause the video and try to find out certain pattern without reading the top part. I have magnified this slide on purpose. So pause the video, think about it, try to find a certain pattern which you are observing in this. Well, some of you might be guessing the corners is a pattern. Some of you might be thinking whole of it as a block, right? So let's discuss it actually. So what does n is to m sparsity actually mean? So n is to m sparsity means that in each contiguous m elements, n of them is pruned. And a classic case of it is that for every 4 elements, 2 of them are pruned, and this is what is happening. For every 4 elements, 2 of them are pruned. For every 4 elements, 2 of them are pruned. For every 4 elements, 2 of them are pruned. So this is what the pattern, what we are observing, and this is known as 2:4 sparse matrix, and this is a very good pattern. And this 2:4 sparsing of a matrix multiplication, because ultimately what do you do with the sparse matrix? You have to multiply it with maybe another sparse matrix, or multiply it with maybe a dense matrix coming from the input, right? So ultimately we have to perform the multiplication. So for that, what we can do is, for 2:4 sparse matrix, we can represent it easily with this way. We can represent all the non-zero values in a much smaller, compressed, 50% smaller matrix, and along with, so each of these values are what, FP32 right now, because we have not done the quantization as yet. So each of these are 32. So directly we've reduced the model size from, if it was originally 14 GB, 15 GB in, let's say, some large language model like ChatGPT or something, Directly we reduced it down to 7.5 GB. And then based on the matrix multiplication, whatever we are doing, we just have to store the 2-bit indexes, because which two non-zero values are being used, that we have to specify, right? So how to specify the two positions of that? Using a 2-bit indices. Using 2-bit index, you can specify 4 locations. So that's how you're maintaining that. So rather than storing 32 bits, we are just, instead of that, storing 2 bits in a separate matrix. So this is the compressed matrix representation, and it is supported in NVIDIA's Ampere architecture, and it can deliver up to 2x speed for BERT models or something similar to that. Let's look into some cases of pattern-based pruning of NS2M sparsity. And we've already described all this, and it usually maintains accuracy, and it's tested on varieties of tasks. So on ResNet 50 with the ImageNet data set, and the metric we're choosing is top 1 metric, like error basically, top 1% error. So dense FP16 76.1, sparse FP16 76.2. For ResNext, again on ImageNet data set, the accuracy is almost the same. For exception network, again you will see similar accuracy is maintained. For single shot detection on COCO data set, with matrix as the average precision, AP stands for average precision, BB I am not able to recall right now, so that's also it is maintained. And for phase sequence transformer, you will see that again this thing is maintained, the metric which they are choosing. And for BERT large language model on a SQuAD dataset is Stanford question and answering dataset. It's a very famous dataset which has Wikipedia articles. So in input they have given Wikipedia articles, and along with that there is a question which is there. So it's a labeled dataset. So given a Wikipedia article and a question along with that, in the labeling they have marked the answer particularly from that page. So it's a crowdsourced thing, that if there is a question, where exactly to find the answer for in that page. So this is how you train like your large language models or something in that sort. So this is a very famous data set for question and answering data set, and this also was maintained using this NS2M sparsity, 2:4 sparsity. On the other extreme, we have channel level pruning, which is very easily accelerated, but the accuracy will be very bad. You cannot prune much, like your pruning ratio itself will not cross around 10-20%. Here it can cross around 80-90% as we had seen previously. So pruning at different granularities, let's look into different cases in channel pruning. So there is a direct speed up due to reduced channel numbers, leading to a neural network with smaller number of channels. And after pruning and deciding the sparsity ratio, again how to decide that sparsity ratio is another topic, but assuming that we know the sparsity ratio, we can reduce the number of channels in different layers. So these are the different channels, like the input is coming from here, first it's going through layer 0, then layer 1, generally it has RGB, 3 channels in the input image, and after that, so this is where the RGB image is going inside, and then the number of channels which are there in different layers. So this can also vary. Here we have just chosen to show it in uniform way, but across different layers the number of channels might increase or decrease, and how much from this original point, from this channel to reduce number of channels, that is determining your sparsity ratio. So almost we are doing the half of it. So, and how to find sparsity ratio for each layer. So we will discuss later on how to find the sparsity ratios, and it's an important thing. But what is the appropriate way, how much to shrink, how much channels to reduce, that is another optimization problem. So many of the research papers which people write are related to in machine learning optimization are quite mathematical in nature, because they try to automate this process, that what should be the ideal sparsity. And here's a graph which was published, that on x-axis we have latency and on the y-axis we have ImageNet accuracy. So definitely we want low latency but high accuracy, and this is where we want to be. So given any machine learning model, we want to perform an automatic pruning methodology, in which the model is becoming lesser, like coming on this part of the graph where it is having very less latency but is able to maintain the accuracy high, and that is how you determine the sparsity ratio, by using this mathematical optimization. So next we'll be looking at determining the pruning criteria, that what synapses / neurons should be pruned. And so if there is a node, a neuron, and these are the inputs which are coming from the synapses, basically the W0 X0, W1 X1, W2 X2. If I ask you to prune, like reduce the, if you have to choose just one weight, which weight would you reduce? So intuitively the smallest one, and so the criteria is simple, that the magnitude, whatever is having the lowest magnitude. In this particular example, if it is 10x0 minus 8x1 plus 0.1x2, so x0, x1, x2 is not in your control, right? They can be anything based on the input which is coming. But definitely whatever the value of x2 is, it will be reduced heavily because the value of this W2 is small. So W2 is what we will choose to prune. So the first criteria is the magnitude based pruning, and in magnitude based pruning, consider weights with larger absolute values are more important than the other weights. And for element wise pruning, this is good, that we assign an importance score which is nothing but the magnitude of the weight. So if, as an example, that if we have 3, -2, 1 and -5, then we calculate the L1 norm. L1 norm basically means calculating the magnitude of it, and based on that we'll choose the most important ones, which is the higher ones. And this is what is actually in the mathematical optimization what we had chosen, that if our WP L0 norm of weight matrix is less than equal to 2, then we can just keep, like 1 or maximum 2. So we'll choose 2. Why we'll choose 2? Because that is giving better accuracy, because the main objective function of our mathematical optimization was to reduce this argmin L, which was a function of x comma WP. This is what we had to actually reduce here, right? So it can be 1, but if we choose 2, because this is the criteria, subjection criteria, then we'll get a better accuracy. So we'll definitely want to keep 2. So in this case it will be 3 and 5. So finally the prune weight would look something like this. And there is always a trade-off between effectiveness and how easy to calculate and integrate into product. So this magnitude based pruning, like any class 10th 11th person also, you tell them that okay, this is the thing, just do that, and they'll come up with magnitude based pruning, because it is so effective and at the same time so easy to calculate and integrate. Next is so magnitude based pruning considers weights with larger absolute values. We can do row wise pruning. The L1 norm magnitude can be defined as follows. So we can assign, so this is another criteria in which you can define an importance score, which is based on summation of certain elements based on a structural set. So this is structural set, in this case is the row wise structural set of parameters W. So we'll just do the summation of all the weights in that, the magnitude of the weights. So L1 norm row wise, this time not element wise but row wise, and we assign the importance score 5,6. So whatever is more important will have a higher score and we'll keep that. So we'll keep this row as it is and this row will be pruned. For row wise pruning, again we can do an L2 norm which can give us a different set of results, or maybe the same set of results based on like the weight matrix, but this can also be used as the criteria, that we can calculate the L2 norm of the whole row, and based on that whatever is having the higher score we can use that. So generally L2 norm gives better results than L1 norm. We can have another higher definition of LP norm. LP norm is defined as the summation of the magnitudes raised to that power p and whole divided by 1 by p. So in L2 if it was 2, so you could see that it was having a structure like under root of a square plus b square kind of a format. So you can generalize it to an LP norm, and what gives better results is again like hit and trial or something. But L2 norm generally gives better results than L1 norm. But when it comes to convolution neural networks, all this thing was what we are doing is true for weights which are of the format of C0, comma Ci. So always remember this, that C0 Ci is for fully connected layer, FC layer as we call it. But in CNN layer we have four things: CO, Ci, and kernel height, kernel width. So we have much more margin to play with and different things we can calculate. So we have a better approach for pruning in convolutional neural networks, and what we do is that for every weight we calculate something which is known as a scaling factor, that channel scaling factor. So the number of weights is equal to the number of channels in the output. So this is the output we have, right? And the scaling factor is multiplied to the output of that channel, and the scaling factors are trainable parameters. So you can calculate for every filter this parameter, and based on this, whatever is the lowest, you can prune that. Like 0.1 and 0.29 is the lowest, so we can just prune that. And effectively pruning, that means we are cutting this entire channel off. So the entire channel is being reduced, which directly affects the performance. Like it directly increases the performance because the whole channel is gone. It's a very structured thing. So the scaling factor is associated with each filter, and the scaling factor can be reused from batch normalization layer. So if you recall that our batch normalization layer looked something like this, and we've not gone into mathematical nitty-gritties of how batch normalization actually works. But with the batch normalization thing going on, and again this will be clear to you that just by using the batch normalization we can figure out the scaling factor. So in interest of time, like there are certain slides which I'll be covering in another bonus sessions, but this is pure mathematics which helps us to, it's a second order based pruning, and we'll cover that separately. So what we are trying to determine here is basically this loss function. Sorry, this the induced error by approximated by a loss function. So we're having the original loss function with this, and the loss function based on the same input but with variation created in the weights, the prune weights basically. Based on this we can make certain optimizations. We are not going through them right now. You can just read the slides as of now, but we'll cover it in some bonus recording, bonus sessions. This is not exactly the part of the lecture which I'm trying to introduce here. But point is that in second order based pruning we again calculate this important score using a Hessian matrix, which is very difficult to compute. So, but this gives us good results sometimes, and it's much more difficult to calculate, but gives more effective pruning rather than a very simplistic pruning methodology. On the other hand, when we have to actually, rather than pruning of weights, if we try to prune the neurons, we have to select which neurons to prune, and for that we can choose, when removing neurons from a neural network, the less useful neurons being removed is what we want, the better the performance of prune network is. So neuron pruning in linear layer, all the weights associated with that are simply gone. So it's like basically a very structured regular kind of a pruning. The whole weight matrix is gone. So again it directly leads to increase in speed up performance because it's a more regular coarse grained pruning. And when we do the same thing on channel pruning in convolution layer, so the filters which we have made, entire filters, they are gone, because some filters in some layers, although we have chosen, like in AlexNet, if you remember, in the first year we chosen 96 kernels, but out of them certain kernels are there which are giving very less performance, and like they are not actually helping in the entire structure. So this was a design choice made by them, but which 96 kernels, out of which one to prune, that is the case which this pruning technology or the criteria of pruning is helping us solve. So the entire channel itself is pruned, and all, like if you remember, in this dimension we had Ci. So if Ci is equal to 3 and Co, because 1, 2, 3, 4, 5, 6, so Co is equal to 6, and therefore in outputs they are totally if you have to look it in this direction, 1 2 3 4 5, like we have reduced 2 of these here in the dimension, so you can just break it and understand that there are total 6 dimensions. If you break it, like these lines are not drawn properly, I'll probably erase it, and since I've already drawn it, so I'll just give you more clarity what it exactly means. So here is 1 2 3 4 5 5 6, so 1 2 3 4 5 6. So these was the original. If these were not pruned, then we would have obtained this sort of a channel dimension in CO equal to 6. But now since these two kernels are entirely pruned, therefore 2 of these outputs are gone completely. Now percentage of zero based pruning. This is another technique in which the ReLU activations will generate zeros in the output activation. What it does is that if your batch normalization, if your batch is 2, then how you calculate, and this is the output activation, and height and width is 4, and there are 3 channels. Basically you can consider this is somewhere in the middle, not RGB, but somewhere in the middle. Like in the previous layer there are 3 kernels, and for each kernel this is the output for image 1 and this is the output for image 2. That's what batch 2 means, right? So you can calculate average percentage of zeros. So how you can do that? Like mathematically also you can define it, but best ways to actually understand physically, like using an example how to calculate it. So if there are in the first channel, this is channel 0, channel 1, channel 2. So in channel 0, in the first image, how many zeros are there? 5. In image 2, 1 2 3 4 5 6 6. And total how many of them are there? 4 into 4 into 2, so 11 by 32. So this is the average percentage of zeros. Similarly you can calculate for channel 1 and channel 2. And whatever is the lowest, whatever is this average percentage of zeros is highest, you remove that. So because it's defining the percentage of zeros, you remove that. And lastly we have a regression based pruning. So I think this is regression based pruning is the last thing which we are going to cover. So we try to minimize the reconstruction error of the corresponding layer outputs. And again let me see if we can cover this right now, or alright. So this also regression based pruning, ultimately the loss function which is formulated and the subjection criteria. So regression based pruning also we will cover in a bonus lecture. So second order pruning, second order based pruning and regression based pruning we will cover in a separate lecture. So this is the summary of today's lecture. We discussed what is pruning, the granularities of pruning, the criteria to select weights to prune, and so in the next lecture maybe we'll just skip the pruning part for now, and in the bonus lecture along with something we'll take a pruning topic once again towards the later part. But we've got the basics of pruning which is required for us to actually deep dive into the deployment. So next lecture would be about neural architecture search for now. So thank you so much for watching this video. I hope you understood the concepts. Thank you so much.